Let us now look at some properties of the dimension. And let's for now stay with the dimension of a ring. So the first proposition states that the codimension of a prime ideal is equal to the dimension of the localization at that prime ideal. This is because we have a one-to-one correspondence between prime ideals in R that are contained in P and prime ideals in Rp. Because remember, when you localize, we have this correspondence between ideals that do not intersect our multiplicative set and ideals in the localization. And our multiplicative set, when we localize with respect to the prime ideal, is everything that is not in the prime ideal. And because of this one-to-one correspondence, these chains of prime ideals contained in P that are exactly used to define the codimension of P exactly becomes the chains of ideals in Rp, the localization. Also, the dimension of R is a codimension, or the supremum of codimensions. Namely, the dimension of R is the supremum of all codimensions of maximal ideals. Or if you wish, by the previous point, the supremum of the dimensions of localizations at such maximal ideals. Meaning that it's enough to consider maximal ideals when you do this. So the reason for this is that if you have, so of course from the definition, it follows that the dimension of R is greater than or equal to the codimension of P. This holds for any prime ideal P, so pause and think why this is true. Well, going back to the definition, you will see that if the codimension of P is, say, n, this means that we have a chain of ideal, an ascending chain of prime ideals contained in P, and so in particular we do have such a chain of ideals in R, and so the dimension is at least this. And conversely, the dimension is in fact equal to it, because if the dimension of R is now n, so then we have our chain like that. Well, then this Pn is contained in some maximal ideal M, and so therefore the codimension of M will be at least n. So we have equality. And this means that dimension is a local concept. The dimension of a ring is the supremum of the dimension of its local rings. That's one way to put it. If you think about these as rings of coordinates of varieties, this says that the dimension of an affine variety is the supremum of the codimensions of its points, because points correspond to maximal ideals. And in our example, we saw this. We saw that in this variety that consisted of a plane and a line, there is a point that has codimension 2. One other property is that the dimension of the ring can be decomposed in the following way. It is greater than or equal to the dimension of the quotient ring by P plus the codimension of P. This is for any prime ideal P. Why is that? Well, for the codimension here, if this codimension is, say, M and this codimension is n, what does this mean? This means that here you have a chain P0 to Pn contained in P. And here you have a chain, say, Q0 to Qn in R mod P. So finally you have this containing P. And so concatenating these chains, you get a chain of the desirable length, at least in R. And that's why the dimension of R is at least that big. To show equality, we in fact need one further assumption. So if the dimension of R is finite, and every maximal chain of prime ideals has the same length, then the same holds for R mod P, meaning that R mod P also is finite dimensional, and every maximal chain of prime ideals has the same length. The proof is an exercise using the going back and forth between ideals of R and R mod P. Under these assumptions, we now know that the dimension of R is equal to the dimension of R mod P plus the codimension of P. And the dimension of R is the codimension of any maximal ideal P, or the dimension of R mod P for any maximal ideal P. Point 5 here follows from the assumption and from point 2 here, because we know that the dimension is the supremum of these codimensions. But now, since all maximal chains of prime ideals have the same length, we in fact have equality. The proof of part 4 itself is left as an exercise, and in fact the statement that R mod P satisfies this finite dimensional and same length property you can prove more or less in the same go as this statement 4. And the key is again that prime ideals of R mod P correspond to prime ideals of R containing P. We will prove this by working entirely in this ring. So we will be on the ring theoretic side. So we want to prove that the dimension of this ring is n, and any maximal chain of prime ideals has length n. And we'll prove this by induction on n. So the case n equals 0 is clear. Let us consider the case n greater than 0. And we want to prove that if you have a chain of prime ideals, P0, P1, and so on to Pm, then m is not greater than n, and m is equal to n if the chain is maximal. Okay. So by possibly extending the chain, we may assume that we start at 0. If we can prove these facts for a bigger chain, then we're still fine. So we can extend the chain as much as we want. So by extension, we may assume that P0 is the 0 ideal, which is prime because the ring is an integral domain. Also, we may assume that Pm is maximal, or else embed it in a maximal ideal. Intuitively, this shouldn't be surprising, because remember, in the case that R and R prime were coordinate rings of varieties x prime and x, we have seen that integrality means that the map from one variety to the other is surjective with finite fibers. And so this means that it cannot increase the dimension. It is just folding the variety, so to speak. But now we'll prove this rigorously. Before we go into the proof, you might want to pause and think how you would prove this using all the properties of the integral extensions. So let's see how this looks. Let's first prove that the dimension of R is smaller than or equal to the dimension of R prime, feel free to pause at any point and finish the proof yourself. So now we are given a chain of prime ideals in R. This is in R. And we want to construct a chain at least as long of such prime ideals in R prime. But in R prime, I can use my lying over property. So I will find P0 prime lying over P0. Then using the going up property, I can find P1 prime lying over P1 here, and so on until I find Pn prime lying over Pn. So now I have a chain of prime ideals in R prime that are included in the right direction and each lie over one ideal. Why are they distinct? Well, if they were not, then they would not be lying over these distinct ideals. Because remember, when I intersect with R, I want to get back my distinct n+1 ideals here. So this proves that the inequality holds. To prove the reverse inequality, now I start with a chain, maybe let me call it Q0 up to Qn in R prime. And I want to construct a chain at least as long in R of prime ideals. So I take Q0 intersect with R up until Qn intersect with R. This is fairly straightforward and it creates a chain in the right direction of prime ideals. Why are they strictly ascending? If not, this means that more than one of these Qi would lie over the same Qi intersect R. But this contradicts the non-containment property and therefore cannot hold, so they have to be distinct. So we really had to use all of these properties of integral extensions, and then we have established that the dimension is preserved under integral extension. Now the next step is the promised step. So the dimension of affine space, or equivalently of the polynomial ring in n variables. So the claim is, as you would expect, the dimension of affine n space is equal to n. And moreover, any maximal chain of prime ideals in the polynomial ring in n variables has length n. And this was what we needed to finish the proof of the previous corollary as well. We will prove this by working entirely in this ring. So we will be on the ring theoretic side. So we want to prove that the dimension of this ring is n, and any maximal chain of prime ideals has length n. And we'll prove this by induction on n. So the case n equals 0 is clear. Let us consider the case n greater than 0. And we want to prove that if you have a chain of prime ideals, P0, P1, and so on to Pm, then m is not greater than n, and m is equal to n if the chain is maximal. Okay. So by possibly extending the chain, we may assume that we start at 0. If we can prove these facts for a bigger chain, then we're still fine. So we can extend the chain as much as we want. So by extension, we may assume that P0 is the zero ideal, which is prime because the ring is an integral domain. Also, we may assume that Pm is maximal, or else embed it in a maximal ideal. And we will assume that P1 is a minimal prime ideal. Then we have a fact that says that in that case P1 will be generated by one element P, because we are in a unique factorization domain. This is a fact from algebra that we will use without proof. And by changing variables, we can assume that P is monic in the last variable. So this was the same thing we did when we proved the Noether normalization theorem. So now we have the following situation. We are in our field, okay, not the field itself, but the polynomial ring over the field. Then we pass to the quotient ring. Where we quotient by this P1. Then, so we pass from there to there, and then we pass to the polynomial ring in n-1 variables. So here we have our chain that we started with. So from P0, which is 0, contained into P1, which is this P, contained and so on into Pm, which is maximal. Mod out by P, we get the following chain of ideal that starts with P mod P, which is 0, and contains into Pm mod P. And when we go down to Tn-1, since P is monic in Tn, this extension is an integral extension. So here we get the underlying ideals, so sect to get a chain of ideals. So to summarize, what have we done? We started with our chain of length m, which was chosen in such a way that when we factored out the first ideal and now got a chain of length m-1 in the quotient ring, we still, by the relationships between the properties of prime ideals in the ambient ring and in the quotient ring, we still have a proper ascending chain. And then, because the dimension of an integral extension is the same as the dimension of the lower ring, and because this P is monic in Tn, this ring extension will be an integral extension, so the dimension doesn't change. And not only the dimension, but in the same way we see that the length of this chain doesn't change. So in this ring now, we have this chain of length m-1. But now, by the induction hypothesis, we have the properties we want to prove, namely m-1 is smaller than or equal to n-1 with equality if the chain is maximal. And one can show that maximality here corresponds to maximality upstairs, and this proves the proposition. So it's an exercise for you to write down these details to check that they are accurate. This follows from Noether normalization, Because if the variety is x, then the ring, the coordinate ring of x, is integral over k t1 to td. So this shows that the vague claim that I made when discussing the Noether normalization theorem, that this d is somehow the dimension of x, this is indeed the case, because d is the dimension of this ring, as we now know, and so since dimension is preserved by integral extensions, it's also the dimension of the affine variety x. So d is, first of all, well defined in terms of x. It depends on x only, and it is finite. This follows from Noether normalization, because if the variety is x, then the ring, the coordinate ring of x, is integral over k t1 to td. So this shows that the vague claim that I made when discussing the Noether normalization theorem, that this d is somehow the dimension of x, this is indeed the case, because d is the dimension of this ring, as we now know, and so since dimension is preserved by integral extensions, it's also the dimension of the affine variety x. So d is, first of all, well defined in terms of x. It depends on x only, and it is finite. Finally, let us look into this result, Krull's Hauptidealsatz, or principal ideal theorem. The theorem says that if you have an irreducible affine variety and you take a non-zero regular function whose zero set is not empty, then the zero set is a hypersurface in X, meaning that it is an affine subvariety of codimension purely 1, because of the relationships between dimension and codimension that we have seen. The proof of this will go in 3 steps, and it will involve some rigorous statements, some statements you will prove as exercises, and some things we just skip. So first of all, we may assume that VF is irreducible. So now, assume that VF is not empty. We need to show that it's a hypersurface. Why can we assume that it is irreducible? Well, if not, then the first thing you need to show is that there exists an open set such that the intersection with VF is irreducible, and also that the dimension of U of any open set is the same as the dimension of X. This is easy to believe because X is irreducible, so U is dense in X, but you can work out the details yourself. So replace X by this U, and you are looking at a V of F that is irreducible. The second step is to reduce to the case where X is in fact the affine space. Why is that? Well, we know that we have a map from X to A to the power D that corresponds to an integral extension by the Noether normalization theorem. So call this map phi. And we want to find G in KT1 TD with the property that the vanishing set of G is equal to the vanishing set of phi of F. If we can do that, then using the proof of the theorem that integral extensions don't change dimension, we can lift this reasoning back to X and have our result. Finding this G is tricky and not part of this course, but let me indicate it in case you know. So you take as G the norm of F with a certain field extent with respect to a certain field extension, if you know what the norm with respect to a field extension is, namely the field extension of the fraction field of the coordinate algebra over the fraction field of the polynomial ring. But having done that and proved that this is okay, we have reduced to the case where we only look at affine space. The third step is now to prove in the case x equals AD. In this case, our map F we can assume after a change of variables, as in the proof of the Noether normalization theorem, that we can have F monic in TD, in the dth variable. In that case, the inclusion of the vanishing set of our map, well, now it is called G, I guess, into the affine D space and then projecting onto the first D-1 variables. Because of this monic business, this corresponds to an integral extension going from KT1 to TD-1 to the coordinate ring of V of G. And by the dimension preservation of integral extensions, this proves the Hauptidealsatz. Let us end by stating without a proof a converse of this theorem that might be surprising. So the Hauptidealsatz tells you that the zero sets of single polynomials are hypersurfaces. Now, given a hypersurface, will it be the zero set of a single polynomial? The statement says that a Noetherian integral domain, such as the coordinate ring of an irreducible affine variety, such a thing is a unique factorization domain if and only if every prime dimension 1 is principal. So this says exactly that if you have a hypersurface, then it will indeed be the zero set of a single polynomial, provided that the coordinate ring is a unique factorization domain. The proof is omitted.